Good morning. Thank you for making it here at 9 a.m. And apologies for those speakers in the morning. I can't make usually unless I have special arrangements because my kids' school starts at 9. So I end up putting the headphones and start listening to YouTube. Rob Schreiber emailed me saying he's going to be on YouTube. Hi, Rob. And it's a tall order to come from Palo Alto, I think, every day. So I'm going to talk about something it's kind of oxymoronic, modern and sparse linear solvers, because this is a topic from a long time ago. And there'll be a lot of things that are not that modern, and there'll be a lot of stuff that is modern. Sparsity is everywhere, man-made system, nature-made systems. This is kind of what sparsity means. Among all possible interactions, not all of them are present, or not all of them matter. Right? When you're building a bridge and you want to make sure that it's going to survive an earthquake, you don't model every n square little pieces of your finite elements or whatever you're modeling, and not every star has significant impact on everybody else. They do, but it's not important for the actual things. And I love this area, right? In fact, I got my license plate delivered 2 days ago. I forgot that I ordered this because DMV takes about 3 months to send these things, and there's no email, any of these things. It suddenly appears in one day. Brief history, this is not inclusive. I just started in 1990 because I think I was 7 years old by then, so before then it doesn't really matter for me. But I'm going to talk a lot about things that happened way before then. Back then, the whole use of sparsity was PD, circuit simulation, numerical optimization, and then the networks and graph analysis came. I kind of put a landmark there, which is probably PageRank started a lot of those things. Big data, collaborator filtering, Netflix, whatnot, tensors came. There's some landmark for me. Most people don't know this, but Chemical then. I think Brent Bader had this sparse tensor toolbox release, made people easy to play with. Deep learning, graph neural networks, quantum computing, these are the current areas of active research on sparsity. Aparna talked about some of it yesterday. Marianne will talk after me, and I'm not going to talk about here. I'm going to talk about the boring side on the left today, because when I've been asked this, I said, I have 75 minutes. This is essentially a lecture. Let me put together something so I learn on the way when I put together this thing. So it's not a lot of my work, but it turned out some of them are. Lots of figures and slides are gently stolen by a lot of people. Foremost, my advisor, John Gilbert, who taught a semester-long class when I was a grad student on this topic. So I'm trying to compress it to 75 minutes. And he actually, before that, he used to teach 2 parallel ones. One on iterative solvers, one on direct solvers, which I didn't see, but apparently it's on the history books somewhere. But I thought those should be known because it's beautifully made, lots of time has been spent. There's no need to recreate them. Shirley up at LBNL, my colleague, Yan Shang, who's my PhD student in the room, Tian Yu, also a PhD student of me and Jim, both of them. Esmond Ding, who retired from LBNL, and Jim, of course, in the audience, many of you know. So what is really the sparsity? Everybody has an idea, definition, but this is a good one. The property of having few non-zero or significant elements in a data set, matrix, or distribution. It's in quotations because I copied it. I don't remember where I copied it from. And if you look at old papers on this thing, for example, this one, 1988, and if you read the abstract or title, you'll see this thing called in time proportional to arithmetic operations. I wish more computer scientists wrote papers like this. What does that mean for computer science perspective, right? So there is an algorithm that, in the best case, if every overhead is excluded, data structure setup, destructions, initializations, it has to do blah number of operations, but it's different based on input. For one input, it's going to do 10 operations. For one input, it's going to do 1,000,000 operations. And what this algorithm more or less guarantees is it's going to run on that time, no matter what the input is. So it's fascinating, and there's a lot of algorithms in sparse matrices like that. But the theoretical computer science perspective would be to find one obscure input and say, The worst case is blah, so we're going to make an algorithm that matches that, and we're going to call it optimum. Like I have to kind of, and now I'm in this position to kind of complain about some of those things. So here's one. For example, in a research field of mine, sparse matrix multiplication, I worked a lot on this thing. There is a famous work that does this thing in order n squared plus epsilon. It's optimal because you can find two sparse matrices, you multiply them, the output is dense, so it's optimal, case closed. Makes no sense, almost no input pairs will create this worst case thing. It doesn't stop the work from being cited 400 times. No complaint to the authors either, because it's a community problem, right? So take another problem, matching. I'm going to talk about graph matching. Graph matching is bounds, right? M times square root of n, or for the Hopcroft-Koff algorithm, I think. Great, but if in practice it's actually faster in almost all cases you can get your hands on. So you got to know what's going on per input. And some problems it's not important. But the idea is simple. Don't do redundant work. Count the sparse bluffs. Stay as close as possible. What do these guys look like? These are all mostly simulation engineering problems. If you look at problems from networks, the plots look very different. Networks, I mean graphs. But for a lot of things that we solve, linear systems, they kind of look like this. They have some structure. Some of them even more structured than this. But it just gives you pictures. These are a good sample of problems, right? Computational fluid dynamics, circuit simulation, nonlinear optimization, and so on. So what's the problem I'm focusing on? Very simple, AX equals B for sparse A. Important since 1950s. Whenever people developed computers, they wanted to solve this. There is a 2x2 chart. I could make it 3x3. I could make it bigger. But this is kind of, I think, gets the idea. Your input A can be symmetric, positive, definite, in which case you have different options versus when the input is non-symmetric. Things are simpler in SPD, symmetric, positive, definite. And in which case you can use, for both cases, you can use direct or iterative methods. The direct method of choice would be something called Cholesky. Your pronunciation might be Koleski, whatever. And for non-symmetric, it would be pivoting LU. Why? Because if I don't pivot, I can divide by 0. Things can go really bad. This doesn't happen with SPD matrices. And there is a selection of iterative methods and for different inputs. Now, these two axes matter. Obviously, more robust, more general. Non-symmetric is more general. And then for direct methods, if they work, they always work. Because there's a finite sequence of operations that will get you the answers. And we'll see what the problem is there. Why don't you always use that? Question?
Give some definition of robust.
Robust means as long as you have enough memory, it will complete. That's even like debatable. There's some inputs that it can fail. But if you do actual pivoting with goodness to honest pivoting, it will. Whereas iterative solvers might not converge. And in some problems, you might need to spend the whole career building the iterative method to solve that particular system. And people did that. Another question?
Is this like a function of the structure of the problem, or is it about floating point inaccuracy and then issues around that? Like, what is the...
Yeah, why would you not be able to solve this problem, right? Lots of things are in play. For iterative methods, the main issue is something called a condition number would affect how fast you're going to converge. Yeah, I mean, there is proofs that, I will get to that. For example, this thing is guaranteed to converge. Conjugate gradient. In fact, some people used to call this a direct method back in the day because of that. It actually is only guaranteed to converge in real arithmetic. And so your point is correct, that in floating point, it's not guaranteed to converge, but it often does. But why and how, we'll get to that. But the whole process looks like this for a general input, general A. You have the sparse matrix as your input. You usually want to factorize this thing first. To people, the textbook will say LU. Before you do that, you want to reorder this thing. And there's two reorderings often available to you. One is to minimize the fill, and I'll talk to you about what that means. and the other one is for accuracy, so that you don't divide by 0 or anything close to 0. And then you do the factorization, and then you get triangular systems L and U, which with back substitution is somewhat trivial to solve. So you solve it for whatever given B vector is. So, dense Gaussian elimination, well more understood. Actually, a chapter about this in the Corman-Lysensen Riverstein book, right? So, but in general, there's at least 3 different ways you can write this. You can write this more. The right-looking algorithm is the one that's taught most, which is you choose a pivot, you factorize the column, and you update the trailing matrix, the Schur complement update. So you immediately push the updates to the right side of the matrix, and you eagerly do that. This is kind of most people do when they learn how to do Gaussian elimination by hand in a high school or, I don't know, sophomore college linear algebra class. The left and up-looking algorithms are lazy update algorithms, so you don't immediately update the column that you're dealing with. Let's look at the left looking. In this case, when I'm about to factorize this, I look back and apply all the updates I should have updated, applied to this column at that time. So here there's a lot of writes. There's a lot of reads, right? And parallelism is different. There's writes create more parallelism, but more conflicts in terms of, so these are used in different areas. If you want a sequential code, you probably want to write it either left-looking or up-looking. It's really efficient. But if you want to parallelize this thing on distributed memory, it doesn't work very well. So you want to probably use right-looking. But that's all dense linear algebra, and nothing I said actually correct is for dense linear algebra. So I'm actually thinking sparsely. So let's get to the sparse one. What happens? Here's what happens when you're given a matrix and when you factorize it with Cholesky factorization. This is a SPD matrix. I get L times L transpose from A. The original non-zeros are depicted with blue dots. And when I do this thing, I get these red dots. These are called fill. Why does this happen? Imagine you have a whole row of bunch of zeros. And what do you do when you eliminate? You subtract one row from another. If your row has a non-zero, when you subtract it from a row with a bunch of zeros, those things will become non-zeros, right? That's what fill means. So that's the problem with direct methods. How can I minimize the number of red points is a well-known problem, NP-complete, all that stuff. And there's a big industry of, I won't call it cottage industry because it's actually a pretty impactful industry of minimizing this thing. We'll talk about those. They're fascinating methods. So how can I analyze what's going to happen here before I actually do the factorization? I can just do this thing and get the result. But can I actually know what's going to happen in this matrix before I factorize it fully? And it turns out for Cholesky, you can. It's called symbolic factorization. So there's a basic theorem, 1961. And it says, well, if I ever see a non-zero in the factored L, remember L is the factor, either it was a non-zero in the beginning, A, or there was some k that was smaller, such that there is a Lik and Ljk that is non-zero. It might be a little, remember, L transpose. So it's probably easier to think about this as saying Lik and L transpose Kj so that you can put a path together in your mind. And you can prove this very easily by staring at the right-looking code and see what's going to happen. Okay? But then I think Rob is on the audience who proved this or might be proven before. The path lemma says you don't, so this is only one step. There is some k in the previous side of the matrix that is lower numbered k that creates this fill. But you can apply this idea recursively and then start thinking, okay, some Lij will become a non-zero because there is this Lik, L transpose Kj, which themselves are perhaps either non-zero or they also became non-zero from the application of the same lemma. So if you recursively apply the same lemma, you'll get this thing. If there is a path in the graph from V to W such that it only goes through vertices numbered smaller than both V and W, and in this case, I'm using the word vertex to represent a row or column in this matrix, that will become a non-zero in the output. It's only a recursive application of the Parder's lemma, right? So what does that mean? I can figure out what edges will be filled by just working on the original graph and not doing any factorization. Pretty nice, pretty neat. Any questions? It's not very modern, right? 1960s, 1970s, but it's cool stuff.
Just to make sure. So, like normally when we think of a graph, like the numbers on the vertices don't mean anything. They're just names or something. But here the numbers mean something.
Yeah, let's actually show what I mean with graph. So I use the word graph, but here's what it means. I just represent each row and column as a vertex in this thing. And I'm always dealing with square matrices, right? Otherwise, I can't do LU. I can't do any of those things. And there's an edge if there's a non-zero. If you only look at the black edges here, this represents the original graph called GA. G plus A is the filled graph. All the red ones are corresponding to the fills. And so what is happening is every time I eliminate a vertex, let's say I'm going to eliminate 1 and nothing interesting will happen because all its neighbors are larger numbered. I'm about to eliminate 3. I have a neighbor 1, so I can go from 3 to 8 going from lowered numbered vertices. So I'm going to get a fill from 3 to 8 as soon as I eliminate 3. What it really does is it converts your subgraph into a clique if the things that are numbered are smaller around you. So that's all there is. Now, there's a lot of text, but all I wanted to say in this thing related to parallelism is there is a very compact data structure called an elimination tree. You don't even need to apply the path lemma over and over again. You can build this guy, and it will tell you all the dependencies between your columns of the matrix, assuming you factorize column by column. If you do row by row, it's going to tell you all the dependencies. How do you build that thing? If you looked at the filled graph, or you looked at the filled matrix, you would just look down at each column and pick the first non-zero entry that's not the diagonal. That will be your parent in the elimination tree. The crux is, of course, I don't have the factor yet, but there is a very simple way of computing it directly from the input graph or input matrix, whatever you want to call it, in almost linear time. And that, if you were here for Bob's talk yesterday, you will like that function, right? So,
one clarification.
Yeah.
So you mentioned the original A, but it's really after reordering, right?
yes, I'm about to come to the ordering. Yes.
Okay, so it's
Yeah.
not, you have to pick an ordering and then you.
Yes, but let's assume that the order is given, or I'm just using the natural order,
Okay.
right? So, but I can change this. Yes, correct. There can be a reordering. There doesn't have to be. You better do it, though. We'll get there. So if there is that reordering is for usually minimizing fill, right? I apply this thing, and I continue it. After I get this TA, the elimination tree, for a given ordering, I can topologically reorder this guy, which is a separate ordering concept. It won't change the fill. It won't change the operation count, but it can increase parallelism. Any topological order on this beast is going to create the same number of operations. But it can increase parallelism, obviously, because I can work on these subtrees independently. So that's the main idea of parallelism. We'll get to that in a minute. How do you build this thing? It's actually a pretty simple algorithm. I don't like putting code, but when it's 4 lines, I like putting them. It's kind of, right? For all vertices in increasing order, look at your adjacency, but only the lowered number ones. And if the root of that vertex in your adjacency is not pointing to your root, point them to you. And this algorithm will run in edges times inverse Ackermann. I didn't write the full inverse Ackermann. Alpha times E comma something, right? I forgot what that is. But since for is practically constant, I don't really care what the variables inside the inverse Ackermann are. Hopefully you were there, but if you weren't, it's really cool thing.
But that's a sequential algorithm, right?
Yes, yes.
So is this part just so fast you don't worry that it's...
Exactly. But memory is still a problem sometimes. If you're given a 10 billion edge graph, I guess you can still do sequentially if it's almost linear time these days. We are in 2025. Yes. Most people don't parallelize this phase. But I had to explain this thing so that I can show you a work that Jim has done long time ago. So here's the funny thing about this. I looked at this old slide, and I said, I should find a modern version of this slide. But then I realized, why? Right? So the whole idea is, the main idea is the same. This is actually an elimination tree for a non-symmetric thing. But the whole idea is the same. Almost all codes use this kind of thing if they want to schedule operations of factorization on large-scale machines. They find subtrees, and they map them to different processors. And then you need a lot of fancy scheduling algorithms, coordination, and so on. But that's essentially the idea. But what else you can do? You can compute column and row counts on the output in also almost linear time. I'm not going to talk about this. In the Cholesky case, at least. And you can use this as cost weights in your, in your edges, sorry, in your vertices in your elimination tree. So if I know how many non-zeros it would take to form this column, I can use it as some sort of proxy for my weight. It's not great, but it works well. Now I'm going to get to Phil's question of reordering. So this is Harry Markowitz, the first of the two Nobel Prizes I associate with sparsity. The other one is AlphaFold one. This is kind of related, I think. And he said this thing. If I choose my pivots carefully, things will stay 0. And he has a particular pivoting algorithm named after him because of that. So what's the reordering problem? If you are given the same matrix, you can do n square fill. Here's your pathological example, or pretty much no fill, right? If I choose my pivot order correctly, things go very well. But as I said, it's NP complete, and you end up using heuristics. So here's one heuristic. Here's where the things get a little bit parallel, thank God. This is work actually Yansheng has done. Minimum degree has been known forever. Yansheng hasn't invented this. This has been known since eternity. The idea is a very simple heuristic. Select the minimum degree vertex as the pivot at each step. Okay, so what does that mean if you do it in the original graph? This is actually not true. This is not the elimination ordering. We just chose this ordering to illustration. Otherwise, the input graph to illustrate what's going on would be too large. But you just choose the vertex with the minimum degree. But now how are you going to update the degrees fast? That becomes the problem. And don't get too excited thinking that your dynamic data structure would be useful here. I got excited at some point. But it doesn't work like that because these guys are smart. They solved this dynamic data structure problem a long time ago in some way. Still, there's work to be done. They don't actually ever introduce edges to this graph when they eliminate. There's no chords that are actually made and edges inserted. They just mark that vertex now, and they call it an element. And it's kind of like you can think of it, a hypergraph, but it's not really. And now it's as if there was a clique here. Treat this as if there is a clique here. And then your next thing you eliminate, then you merge this 5 with the next big element. So it stays as sparse as the original one. It still has some dynamic updates, but it's not a lot of edge insertions happening. It's called the quotient graph. So when a variable is selected as the kth pivot, it becomes an element, and its neighborhood update rule is you can find it in a lot of papers. Problem, updating degrees is expensive. You need to figure out what to do with set unions, and people figured out, not people, a lot of people in parallel, but in particular, a list of authors, Amestoy, Tim Davis, Duff, I think, Ian Duff, and so on, had this approximate minimum degree. People had different definitions of this. This one works very well. Their approximate minimum degree. And if you Google this thing, it's always going to return their algorithm. So it just approximates the degree somehow using one of the three things. You don't need to worry too much about the details. There's too much mathematics. It's just they don't maintain the degrees exactly. It's a heuristic anyway, right? Who cares? But it turns out actually this version of the approximate minimum degree is better than the original minimum degree in many cases, and no one knows why. Yes?
Yeah. Are there also approximations algorithms or only heuristic? I mean,
Yeah, there is a whole different thing that I don't know. Maybe Rasmus knows a lot more about these things. There's concepts like tree width and so on. I'm not going to talk about them. I'm going to talk about when you go to an industrial strength solver, what's happening is what I'm telling mostly. All right, so how can I extract parallelism in this algorithm? Now I'm actually in a place where I want to extract parallelism. And you know Amdahl's law, right? If you don't parallelize one phase of a computation, it will come back and bite you. Rapp will say it doesn't matter. But today, if you benchmark solvers with the really fast GPUs that are taking over the factorization phase, you will see that ordering is now 25% of the total runtime, even with a fast algorithm like approximate minimum degree. So, and Amdahl's law says it's only going to increase because the factorization is increasing in performance, and these things are not. So what can we do about this algorithm was the problem start. Well, you can look at, can I parallelize each degree update, like each neighborhood degree updates for every vertex I parallelize? Let's call this intra-elimination parallelism. There is not enough work there. You can just look at these numbers and you'll find that I need to extract a different level of parallelism. Like just using atomics and doing it per vertex neighborhood doesn't work. I can do inter-elimination parallelism, find an independent set. It turns out actually the simple independent set doesn't work. What does that mean, independent set? I don't share a neighbor, but that neighbor, I share a neighbor. I'm not a direct neighbor, right? That's the problem. So I need to update degrees for 2 when I eliminate 1 and 3 at the same time, but that's a contention already. So I need to go to something that's one level up, which is distance 2 independent set. That means not only, I don't share, not only I'm not neighbors, but also I don't share neighbors. This way I can update the degrees of my neighbors independently from me. But this is a tall order too. There is not enough vertices in MIS2. Question?
So is the bottleneck here like literally contentional atomic variables of the shared neighbors? Or
That would be one.
Okay.
Yeah. So this one solves it, but it's still the sizes of these MIS2 sets are not that large. So what we did here is relax the definition of minimum degree. Why is this not big? Because you are constrained, but in addition to MIS, you're choosing MIS within the vertices that have the lowest degree. There are already a small number of them, right? So we relax the definition and say we're going to allow some percentage, like 10%, 20% of the minimum will be in the set of things that I can choose to be in the MIS2. And that kind of works well. So that's one thing. That's the multiplicative factor. You can look at the sizes of the maximal distance to independent sets when you relax this thing. And you'll see that by just going 10% more, you're an order of magnitude better in terms of the amount of parallelism you can extract. And then we do multiple minimum degree with this AMD thing, with this approximation. With all these parallelism combined, lots of details, how to update the degree lists, quotient graphs, you can find it. And it actually gets you speed up over something called sparse, which is the fastest thing you can get for this problem. In fact, again, coding Rob again, so you'll be crazy to compete with Tim Davis in performance if you're writing sequential code. So the baseline is strong, right? So, and then the improvements are overshoot sparses can be up to 8x, depends on the matrix size. Not too bad. And the fill-in is not increased significantly. We're talking about, there is a little bit of increase because I relaxed the definition. Yeah.
How large are those data sets?
These are, you'll have to look at them. They go up to 500 million max, non-zeros. That's the NLP 240, I think. But we just found bigger matrices from someone in Italy that put their 3D problems that go all the way to 10 billion now, and we're going to see what we can do. The problem with this thing is, let's be perfectly honest, so everybody in the room understands the issue. If I am using this solely for direct methods, how am I going to factorize a 10 billion matrix directly on any computer unless it's biggest supercomputer anyway, right? So, and I'll get to the numbers. But luckily, this algorithm is applicable to a lot of other things. In fact, my colleagues, David Gleich and a student, Mark Tunnell, did a lot of iterative solvers experiments. And they found AMD to be one of the best to apply before doing the iterative solver, against the conventional wisdom. So you can apply these iterative solvers as well, in which case it would make sense to work on 10 billion non-zero matrices. But for a direct solver, it's a little bit of a big size. OK, it scales well, blah. But in practice, do people use AMD for large-scale inputs? And to be honest, they don't. They use a combination of nested dissection and AMD, or plain old nested dissection. So nested dissection is the alternative method, if you think about this. It goes back even earlier, I suppose. No, it doesn't. It's Alan George's idea. So what does it say? I'm going to choose a separator in this graph. It's easy on the grid. And I'm going to order this matrix in such a way that the things on one side of the separator are ordered first. The things on the other side are ordered second, and the separator ordered last. Recursively apply this idea. If you're looking at the input, it looks like this. But if you're looking at the output, meaning the Cholesky factor, if you apply this thing, it will have this completely dense S. And then dense sections like this, somewhat dense. Why is this completely dense in this little s? Path lemma. I numbered this thing the largest, so I can always find a path through smaller vertices, right? So this is going to be completely dense when I factorize. But that's not a big problem as long as I can keep my separator small size. And the good news is this is going to be completely empty, the off-diagonal blocks. Why? Path lemma. S will block any fill because it's numbered larger than anybody on both sides. And then when I recursively apply this thing, it's going to give you the typical, again, this is a picture of the input, actually. I should find a picture of the output. But you can imagine what's going to happen. Fill here, non-zeros stay non-zero on these areas. OK? And it gives you an elimination tree that is usually shorter, well-balanced, and fatter. So everybody should use nested dissection, right? Anyone knows why it's not case closed? There's one reason, which is this is significantly slower than AMD, because you have to find graph separators. You have to find graph partitioning, which doesn't scale very well, because graph partitioning is a chicken and egg problem to do in parallel, right? So in this graph, it's easy. It's a grid. But if you're given an unstructured mesh, unstructured problem, finding good separators in parallel is a challenge. And it takes time. I actually did this thing. So I started plotting how different this looks. So here is three matrices that were in the first page of our paper. And I ordered it with approximate minimum degree. I ordered with nested dissection. Here is after ordering, they look like this. And I plotted the elimination trees. I expected the nested dissection to be better, and it is better. The numbers are not that visible, but this is 4,000 something, this is 8,000 something. But it's not that much better. I thought AMD has no explicit goal of keeping this thing balanced. It would basically suck. But it doesn't suck that bad, right? It still has a lot of parallelism here, to my surprise. But if you don't reorder, the elimination tree would have height so high that you would have no parallelism. The height of elimination tree, you know the work span model, you can think of the maximum parallelism as the amount of nodes in your elimination tree divided by its height, which would be less than 2 if you didn't reorder. But once you reorder, you're in the realm of 100 plus, which is not bad. Another matrix, they also look very similar, to my surprise, right? I was expecting to see completely different plots for AMD. So this is another matrix. Once again, nested dissection is nicer for your output. If you're a scheduling algorithm, you would want this, not the other one, because it's explicitly constructed to be that way. And more, right? So you can look at them. This here is a little different, but you see the very typical nested dissection pattern here. In all cases, if you don't reorder, you have no parallelism. It doesn't really matter, because if you don't reorder, you'll get so much fill that you won't be able to run this method. So, OK, so this is the end of the reordering phase. But I haven't solved one little problem called Lx equals b, which is the lower triangular factor. I factorized the matrix. I said it's trivial. There's many modern work here. There's a lot of papers you can find, one-sided communication, 3D parallelism, GPUs. So, but what's the main issue? Writing the code of L \b, which is Lx equals b, is trivial. It's 4 lines. You just start from one side. You subtract this thing from the equation here if you need it. In this case, I don't. And I keep doing it this way for L. For you, it's the opposite. I start from here and back substitute. Well, this gives you a set of dependencies, right? So in order to find the answer of this equation, I don't need anything. But in order to find the answer to the third equation, I need to first solve the first equation. Right? That's the dependency structure. And it's completely encoded in L. Right? If I have L, I can run a breadth-first search and then get this thing called the level sets and do level set by level set parallelism. All these things. That's what most codes do, which frankly is not big enough. And if you're actually smart, you don't even need to generate this thing, because the elimination tree already encodes this structure, so you can reuse this thing. But most papers will assume that's not available, which I find it crazy, because in order to get L, I computed the elimination tree anyway. So that's the parallelism idea. Here's a rundown of this thing. You can use elimination tree. You can discover level sets through breadth-first search. You can do something called synchronization free. So what does that mean, right? I put it in quotations because I have problems with this word synchronization free in this problem. So here's what they do. They look at the in degree of each vertex in this graph. So here's the in degree of 3 is 1, right? In degree of 1 is 0. If you put a graph on this thing, right? And you create an area of this thing. And every time, and then I let my CUDA code go wild. I have a big loop, and I rely on the CUDA scheduler that it's going to try to factorize every column at the same time. Nice. And there is a busy wait here. If the in degree is not, let's put it as 0. Like there's a number there, but if it's not 0, I stop and wait. So someone else needs to factorize the column I'm dependent on. And when this gets to 0, I can continue. So you can call this synchronization free, but I find it insane to think this is synchronization free. So this is kind of like relying on the scheduler to do the right thing and not deadlock, which in CUDA's case works fine, but in general it won't work. But they surprisingly work well. Just to say, this was a good idea for the architecture. It only works in GPUs as far as I know. And then there's 2 more ideas here that I would like to mention. One is, both of them more or less apply to a different case. Color sets. You can color this thing to increase more parallelism, but not in direct solves. You can only do this thing in iterative solves. I'm going to come, hopefully. And there is an idea that you can partition L into a product of L1, L2, L3, all of which have inverses that are not that dense. And that's another idea from 1990s. Okay, so why am I caring about this thing? This seems like way cheaper than factorization, even if it's not parallel. This is becoming a bottleneck due to Amdahl's law, one. And the second one is, often I want to solve with multiple right-hand sides. Think of the problem as an iterative solver optimization problem. And I do have Newton's method. I changed the multiplier. I solved the same structure matrix with a different set of coefficients. And so I don't do a lot of those things. I reuse them. And sometimes you have a bunch of multiple right-hand sides, even with the same numerical values. So this can be done multiple times. OK, so this is the parallelism, the challenging area still. And you will find tons of work actively here. If you want to work here, this is a nice area too. Now, in the interest of time, I think I'm not going to talk about, well, it's actually so simple, but it's not, maybe. I talked about left-looking, I talked about right-looking, and there is modern codes use something called a multifrontal method. It's probably true to say this thing. This is one of the things that people use. And the idea here is very simple to understand from looking at the elimination tree. Right-looking pushes all its updates immediately to everything up from the tree. Left-looking gets all of its updates from its descendants when it's about to be factored. Multifrontal only goes one level on the tree. So what does that mean? I start factorizing this matrix. I basically, picture is better. When I'm about to factorize 1, I have a frontal matrix and I have an update matrix. And I pass this thing to my ancestor, the parent directly, not ancestor. And F2 has the same thing. And the next one, they will merge. So it's the job of 3 to merge these updates to itself. So what am I saying is, instead of reaching out on the elimination tree 2 hops away, I just make it my parent's problem. So then my parent has to deal with passing that information up. So it doesn't go multiple levels. But what does it do as a benefit is you work with dense matrices. That's the plus. You use BLAS3, things get fast. What's the downside? Someone needs to buffer all these pending update matrices, and they take memory. And for a problem who has memory issues, this is the bottleneck. So, but it gives you way better performance in general. Potential parallelism can be either the tree parallelism we talked about in the elimination tree parallelism, different branches, or now you can get data parallelism through MATMOS, right? So 3 levels of parallelism are available. And I'm going to close this section by saying there is also a concept called supernodes. In practice, if you ever hear this concept, it's also pretty simple. The columns of identical structures are called fundamental supernodes. There's no need to treat them separately. You can say that this is one node. And this is actually used in AMD algorithm I talked to you. They're called indistinguishable vertices, and they got treated as one vertex. Same idea. Almost all good codes also use this idea. Cool. Now I want to talk about something that's related to more parallelism, and I worked on very quickly. But hopefully you are too sleepy by now to get more information, right? This is a lot of work. For Jim, and Cheryl Lee has done this work a long time ago in practice, which is super LU dist. So I said in the beginning, in order to solve non-symmetric systems, I have to pivot because numerical stability. But pivoting in distributed memory is expensive. Why? I need to, for each column, I need to look at all the entries in my column, find the maximum entry, move it to the, replace the rows, and I need to do it for every column. So the critical path would be n times log n to at least find the max with reduction. And there's not enough work there to compensate for that span. So the idea here is I just look at the input, forget about the text. I just look at the input, A, and I build a graph model. It's a bipartite graph this time, not a general graph. One side has rows, one side has columns. There is an edge for every non-zero. And I find a matching on this graph, a perfect matching of the maximum weight. That will create the highest entries to the diagonal. And then I hope that this factorization will not break down if I don't pivot with this thing. Of course, it doesn't have the information of the real-time information the LU generates. So it's handicapped compared to partial pivoting. And it often will fail unless you do something called the iterative refinement, right? But people know how to do this thing, which is to improve the solution. So it's a reasonably good approach. In practice, it's used. Here's the problem here. So most codes will use the sequential algorithm called MC64, Duff and Koster. This is part of the many collections of algorithms from UK, MAs, MCs, you might find them. These are industrial strength codes. But they're mostly sequential. Some of them are multi-threaded. Almost none of them are distributed. But the distributed memory solvers now need to gather the whole input and then redistribute them after running the sequential algorithm. So what we wanted to do is get a parallel version of this thing. And it was really a challenge because one of Jim's earlier students, Jason Reedy, has worked on this problem. And he also realized that the main problem of parallelizing these kind of algorithms like perfect matching is long, heavy tail. You get pretty close to the good result pretty quickly. But to get the optimum, you spend enormous number of times, sometimes, not in every input. So what did we do? We have this succession of algorithms that we developed over years. And then we call them, so this is a lot of text. Let me see if I can minimize this text. In practice, what happens is this. I am given a matrix. I've treated it as a bipartite graph. I don't. I work on the matrix directly, but conceptually. I find the maximal cardinality matching. This is very fast. Maximal is not optimum. Fine. But it's a good warm start to do a maximum cardinality matching. And we have different papers on this thing, how to choose augmenting paths using distributed memory sparse matrix operations. And then from there, I find weight increasing short alternating cycles. But I say I limit this, 4 or 6. I set the number. I only look that long. So that means this is going to be the maximum number of depth I'm going to go in my algorithm. And it generally works fine. We call this the heavyweight perfect matching. And this is, when you plot it, it's pretty good. Like using MC64 plus gathering the matrix would take time red curves. And it's maybe hard to see because too many inputs there. But our parallel heavyweight perfect matching often scales pretty good with up to thousands of cores at a time. But then you can say how good it is. Yes?
If you do this, just do short augmenting paths, do you stop because there are no more short augmenting paths, or you just run it a certain amount of time and say that's good enough?
I explore all fixed length cycles. Yeah, but I fixed length. I don't go deeper than that. So I don't go chase down this order n augmenting path, which would kill my performance. And the approximation ratio is pretty close to 100, a lot of the inputs, except one input. This input actually doesn't do well, even if you find the perfect output anyway. So it's kind of interesting. But this is not the end of the story. So if you're writing a paper here, you shouldn't stop here. You should also look what it means for the solver to have 99.98. That might matter, and in ways you don't know. So just run the solver with this particular, particular matching you got. And we did that. I'm not including it. Now, I am done with direct solves. So much headache, maybe, but here's the picture maybe I should have put in the beginning. But if you're given a well-shaped finite element mesh, either in 2D and 3D. Rule of thumbs are this. You're going to get fill of log n in 2D and n to the 1/3 on 3D. Okay, n to the 1/3 for a 10 billion. Oh, that's non-zero count. That doesn't matter. But still, a big matrix, that can be a big factor. So you get, in practice, fill for really large matrices a factor of 50, even with a good ordering, like nested dissection. So if you have a 10 billion matrix, if you have successfully factored this with a good ordering, what does that mean? You would have 500 billion non-zeros. That's a bit of a tall order. And then you would have a lot of flops to factorize that thing too. So you're in kind of trouble. This created iterative solvers, right? There is a whole, this slide is attributed to you, Jim, but I don't know if it's true. But it's probably coming from the templates for iterative solvers book. You have options. If A is symmetric, you do something. If it's definite, you do something else. Let's not worry about these options. You can read about them. But I just want to talk about something simple, right? This is have you heard the concept of Krylov solvers? Some of you. I mean, of course you did. You don't count. Computer scientists often don't. Okay, there is an old theorem, which I'm only going to state the implication, that says the solution will be in the span of this beast, A, B, A square B. That's the Krylov subspace. And you can get that result by looking at a known theorem called Cayley-Hamilton. Okay? So that's why people search on that space. And this is in contrast to earlier iterative methods called Jacobi or Gauss-Seidel, which are not Krylov solvers. But here's the most famous, maybe, the Krylov solver, which is the conjugate gradient. It kind of looks like this. For the purposes of parallelism, I want to just highlight the computation here. 4 vectors only, 1 matrix vector product per iteration, 2 vector dot products per iteration, very simple loop, right? So, and then it's magical of short recurrences. I don't need to keep track of previous things. And this is only true for CG. In reality, you need to depend on previous iterates. But here, you only need to look at the one before, not any history. So what can I do here, right? I can work on sparse matrix vector multiply for the rest of my life and try to optimize this thing. But in practice, people actually don't use this. They use something called precondition solvers. So what is a preconditioner? Without preconditioning, this can take a long time. Or in general iterative solvers, things can take a long time. So preconditioning is this simple idea that what if I had a separate matrix B such that when I multiply its inverse with A, the original matrix, my condition number, who basically determines how fast I'm going to converge, would be down, smaller, right? So, well, 2 pathological cases. I want 2 things, right? One is this condition number small. The second one is I want the factorization with B easy. Well, if I take B equals A, I will solve it in 1 iteration, but then I degenerate it into direct solves. If I choose B equals identity, then I didn't make any progress in terms of my convergence. So you try to choose something in between. And there's a lot of methods here, but in code it looks like this. You insert a preconditioning solve somewhere in the middle before you choose your search direction and apply your improvement. One of the most general techniques, which is, I think Edmund Chow talked about this thing a couple of weeks ago, and tried to contrast this with approximate Cholesky factorizations. You do something that looks like an LU, or IC, which is, you do, or Cholesky, but you ignore all the fill. You say, I'm only going to put non-zeros in the output if they existed in the original structure of A. That's the so-called incomplete Cholesky or incomplete LU 0. And then there is variants of this thing that allow a little bit more fill, depending on the values or other things. Yeah, so the storage is small. It usually runs pretty fast. There's no fill. But it only usually improves condition number by a constant. So here is where a few new ideas I'm going to mention in parallelism area. So this is not new. People did graph coloring. Rob Schreiber again told me that red-black ordering came from 1982 when someone walked into his office. I forgot the name, Weipeng. Which is to say, remember, I said that the parallelism will come in triangular solves from elimination tree or level sets. But here it's different because there is no fill. I ignored all the fill, so there is less dependencies in the vertices of the graph. So I can extract more parallelism, and I do that by graph coloring. People have been doing it for a long time. And if you're a linear algebra nerd, you would know that reordering a matrix would not change the convergence of an unpreconditioned system because it's determined by the eigenvalues, and symmetric permutation is an orthogonal transformation which doesn't affect the eigenvalues. But where you are reordering a preconditioned system, things are different, and not everybody knows why. It's poorly understood, to say the least, but it generally hurts the convergence. But it increases parallelism so much, people are willing to tolerate the convergence that's slowed down. So they still do this graph coloring idea before triangular solves in preconditioned systems. So recently, meaning within the last 10 years, the second citation should also say 15, not 25, sorry. Edwin Chow, and in one case with Hartwig and Jack Dungara, this is separate papers. They came up with this recent ILU or IC ideas. The first idea is very simple. He basically says, forget Gaussian elimination. What if I looked at this problem of computing a factorization like this, where I know the structure of the factors as a set of equations, where each equation is just saying, when I multiply that row of L with that column of U, I get the Aij. That's one equation, that one constraint. And I have about the same number of unknowns as the number of equations I have. It's a nonlinear system. So you should be crazy to solve n nonlinear equations, not n and z of nonlinear equations, instead of a factorization. But it actually beats it sometimes, because there is so much more parallelism in this thing. And the triangular solve is bottlenecked by parallelism. So this is kind of crazy. You can do so much more work, but still be faster. And this is, of course, this also works for one reason, because I don't need to solve this thing all that exactly. Because these things are put as a preconditioner. So it doesn't need to be exact. And Hartwig and Jack and Chow took this idea that this doesn't need to be exact a little further and said, well, why don't I directly solve Lx equals b in an iterative method, like simple iterative method like Bloch-Jacobi. It works as well, and more parallelism. There is no triangular solves. And this is all hinging on the idea that because this is a preconditioner, which is an approximation to the system, it doesn't need to be solved exactly. So just that if you're confused when you're reading the literature, this is what's going on. And there is more. So basically, there are a lot more preconditioners than I can cover. So I'm going to stop here in terms of preconditioners, except this novel work by King and Sachdeva, is that how you say it? Yeah. So here's their preconditioner. Or you can use this as a preconditioner. I don't know if you guys call it preconditioner. It's an approximate Cholesky, except instead of forming a clique every time you eliminate a vertex, you sample a random spanning tree. I think this is the second of papers. The first one wasn't sampling a spanning tree. It was just sampling edges independently. So you get a significantly sparser output, right? And in expectation, this more or less does the same thing, in expectation. And then you can use this thing as a preconditioner for so-called Laplacian systems. Just to set things up on expectations and reality, this is the hierarchy of matrix classes. Of course, there's more, but some of them. I talked a lot about LU and so on. It's up here, everything. You can solve everything with it. And then in this tree down there, somewhere there's this graph Laplacians. So again, I'm solving a very important subset of problems, but it won't solve all your problems, right? So what we did with TNU with PhD students who was working with Jim and I is a parallelization of King and Shestov algorithm, which is different than another parallelization you guys have done, which is this SPA paper where I think you find, I'll let you talk about that. It's quite different. This one is basically a high-performance implementation idea, which is instead of all this symbolic factorization machinery that is really elaborate, I can't predict fill because I don't know what spanning tree I'm going to sample until runtime. So I'm going to use what's available to me on the GPU. So I'm going to use this persistent kernels. I think Aparna was saying yesterday, scheduling becomes a user problem. True. But it's also an advantage. So we can do this dynamic dependency tracking and scheduling in real time. And that will allow us to exploit additional concurrency. So because I'm not creating full fill, I have more concurrency, less dependencies on columns. And I can just exploit them in runtime with this dynamic scheduling idea. And then I don't need to do symbolic factorization. So these numbers are scaling on CPUs. That's good. But the title says GPU accelerated, so that means there must be a GPU result, right? But let's look at the CPU results. Too much data, but it's faster in CPU in general to stuff that we compared, including incomplete Cholesky, CG, and Hyper, which is an algebraic multi-grid code. And in GPU, it's faster than Q-sparse's incomplete Cholesky, but it's, I would say, when you compare it to a really fast algebraic multi-grid code at AMGX, it depends on the input. Sometimes we're significantly slower, like in the first case. Sometimes we're significantly faster, like in the last case. So it's, jury's out there, and we can work on improving that. So which makes me maybe wonder, what is AMG? How many of you know AMG? You don't count. Okay, luckily that's going to be the last thing I'm talking. Okay, reminders back to what we said. Complexity of linear solvers. Now I'm adding iterative solvers. Dense Cholesky, sparse Cholesky, CG with conditioning, no CG. There is this magical thing at the bottom called multi-grid. So what is this, right? Order n. But this is also similar to, not quite like Laplacian solvers. Multi-grid is a technique that works very well on the problems it works and doesn't work outside. So it's not, they will not claim to solve all your problems, right? But when it works, it's magic. And the idea is that it started, I think, a long time ago when people looked at these non-Krylov iterative solvers. And they said they smooth out the high-frequency error fast, and they struggle a lot with low-frequency error. And they came up with this idea. If I coarsen my grid, my low-frequency error becomes high-frequency, and I can apply this smoother to smooth out the now error that became high-frequency and project it back. And that worked on a grid, a loss of theory, which is good. And then people came up with this idea to say, what if we apply this thing on unstructured things where I don't have a grid that I can mathematically define that easily? So that came up with algebraic multigrid. So what does it do? Stolen from Livermore website. I basically choose what my coarse grid will look like. I coarsen it, I get the coarse grid matrix. And then I solve with this kind of smoothing things in between and project back. This is two-level multigrid. In practice, it's deep. I coarsen until it's small enough that I can direct solve and project it back. Lots of smoothing in between. And how do I coarsen this graph? You can set up these matrices called, some people call it R, but it's really P transpose. The original graph, which is representing the original system. And the P again, these are called restriction and interpolation matrices. I do this triple matrix multiply, and I get the output. And how do I choose these aggregates? I can use graph matching. I can use minimum independence set, minimum independence sets 2, problem-specific ways, depending on how the error is behaving, so on and so forth. But in general, you need to run this sparse matrix product fast, because it usually, the setup phase takes about 40% of the total time. And it's all spanned here. So I could talk about my work on this area that we did a long time ago, but I think you're overloaded. But you can work on this problem like I did. I enjoy this problem. This also brings us one parallelism aspect I didn't talk. Actually, I'm going to talk about this because it tells you something interesting. You could use either communication avoiding algorithms Jim talked about, which trades off memory with reduced communication, which is something we have done a decade ago. This is the picture of a 3D algorithm for sparse matrix product called SPGEM. And these numbers are exclusively for the restriction operation, these performance numbers, not general squaring nonsense, right? So it's all about, I call it R instead of P, but R transpose A numbers. So they work well. Or you can, there's the problem here, which is this is sparsity oblivious, and they require random permutations for load balance. They destroy locality, and there's a cost of random permutation too. An alternative we did with a postdoc of mine last year is just use the original structure. There's a lot of locality in the input for this case. And do an algorithm that we call sparsity aware. So only fetch things that you need. If you do it naively and try to fetch exactly as minimum operations as you need, minimum entries as you need, you will be limited by latency. So instead, we do a trade-off where we choose a block size and then fetch everything that you need within this block. So what that really means is I do fetch more than I need sometimes, but it's a good trade-off between latency and bandwidth. And if you compare with something that I showed that scaled well, it does way better. Right? Yes, 3D with random permutation scales well, that I showed in the previous one. But this, with no permutation, is orders of magnitude faster sometimes. So scaling is not the only answer. Sometimes the difference is so big that you just want to. And that's the end of it. This is hopefully some morning thoughts for your next project.
Time for a few questions.
Phil.
So maybe primarily on the last thing, but maybe it's implicit in what you've been telling us, but I didn't hear anything about spatial locality, like you wanted to somehow order the rows, the columns in such a way that you got like consecutive blocks of elements so you could just
Yes.
grab them as one.
Yes. For this problem, we actually have a paper coming in SC that does that, which tells you like if I get similar rows together
Yeah.
in the first matrix, right? They will fetch the same rows of the second matrix when they multiply, and that increases my locality. That's the only thing I can play with anyway in this algorithm. The total number of data access here is number of non-zeros here, number of non-zeros in the output, and number of non-zeros are here multiplied with how many times I repeatedly access this thing. So the how many times I repeatedly access the same row is the only little parameter I can play with, because the rest is just input and output. And I can kind of reorder rows that are similar next to each other, so they fetch the same rows in the second one. Things are on cache or local, except in this problem it doesn't work. In general, matrix products for sparse, there is this opportunity. The way these things are set up, there are no similar columns, which means because the first row tells you, which basically just tells you which vertices in the fine grid are creating the coarse grid in your case. And they will never be non-zero ever again. In this particular version of AMG. There are some AMG where overlaps are allowed, but it's just this particular special case doesn't allow any locality. But in general, yes, you can exploit a lot of locality.
And so then it becomes this trade-off between maybe a suboptimal in terms of fill, but better for.
Oh, you're getting to the fill thing in terms of locality in the factorization?
Yeah, any things you talked about today, we were talking
Oh,
about.
yeah, okay. The locality, yes. People have exploited locality, and it goes back to the elimination tree and how I can schedule things so that but the idea of supernodes is even a simple thing of locality, right? The similar columns.
Yeah.
What I described was exact columns, but in practice, people also do relaxed supernodes and say, I'm going to allow some extra operations, so I'm just going to factorize similar columns together. That gives a lot of locality to them. But yes, I haven't talked a lot about locality, but I think I can talk about them for another 75 minutes. There is deep research there as well. Yes, Jakob?
So you mentioned about this nested algorithm that the slow part is actually getting a good partitioning. I was wondering
Which local algorithm, sorry?
the nested by the dissection. You need a good partitioning algorithm, right? In order to
Fast.
Yes.
Fast, yeah. I think, yes, good quality too, because the size of the separator will determine the fill, yes.
I'm wondering, like, is this like the usual graph partitioning problem, or is it, because
Yes.
those
Yes,
have
yes,
are like super scalable solution these days. So I was wondering if there's a twist somewhere there.
No, well, 99% of everybody uses still sequential methods. So there is probably some solutions, but I wouldn't call a sequential algorithm.
Well, yeah, I mean there are like highly scalable. Okay, maybe we can talk about.
Yeah, I know people do it. Like, I mean, in particular, I think another Google researcher, Jim, emailed me about this thing, talked about, I don't know, you guys have developed something that's kind of not. The problem is quality, right? This is not like a real-world power law graph. So there is good partitions. And no one still beats this algorithm called the multi-level method. It's almost like algebraic multigrid. You coarsen the thing, and you solve it exactly and project it back, right? And that thing, I mean, I don't know. The fastest codes I've seen are not all that scalable.
Oh, okay.
There's stuff from Karlsruhe,
Yes.
and there's stuff from Sandia, RPI
The
people.
Karlsruhe folks, they have like trillion edges in 8 minutes. That sounds quite fast. But yeah, we can talk offline.
Yes. I mean, this is something I keep bringing up with my graduate students, like, look at this Kahib partitioner, and they always come back with metis for some reason. You guys can.
More questions? All right, let's thank the speaker again.
The context is, yeah, thanks for the context is like one, we have worked with like